Okay, so I want to start by proving Green's theorem, and then I'll discuss some further developments. And then next time, well, okay. So let me recall what this setting is. So I don't want to go through all the numbers again, but the upshot is this. So we have a curve C of genus G, and we have line bundle L on C of degree. So the important thing is let's take 2G plus 1 plus P, I guess. P without. And so remember then we have these bundles ML. So we have H naught of L. So this is the trivial bundle tensor O of C. So we have the evaluation map, and then we have this this ML is the kernel. And then the essential point for Green's theorem, I mean, again, there's a certain amount of house cleaning to do. But anyway, the essential point is, so essentially what we need is to show that H1 of wedge P plus 1 of ML tensor L is 0. So at the end of the day, this is the important thing to show. OK, so let's think for a minute. We need to somehow get our handle on these vector bundles. So we have these, we have this curve in PR. Yeah, let's remember. So R in this case is, so R is D minus G. The numbers actually are important here. So D minus G is what? Is G plus P plus 1. Okay. G plus P plus 1. Okay. And we somehow need to get our hands on these vector bundles. So what you could imagine doing is let's pick a reasonably general point on R, on C, and let's ask ourselves, how can we relate the M bundle for L to the M bundle we get by projecting from X? So let's note, let's fix a point X in C. And then if you think about it for a minute, so you can look at this L minus X. So that's a new, C is a curve, that's a smooth curve, that's a new line bundle. And then if you, so any point, a point, and then if you think about it for a minute, you get an exact, you want to relate M sub L to M sub L minus P. And M of L minus P is going to be a subbundle, L minus X, sorry, is going to be a, M, I project from X, so that means I'm embedding the curve by the line bundle L minus X. That's a subbundle of M sub L, and if you play with it for a minute, you'll see that the quotient is OC of minus X. So if you take a general point, so that when you project from that point, you still get something globally generated, you get an exact sequence like this. So somehow if we project from a point, this means we can kind of relate something involving L to something involving L minus X. And so this is a smaller vector bundle. And if we take a bunch of points, so if we take points x1 to xr minus 1, so that's r minus 1 is what? Is x of g plus p, is that right? Yeah. If I project from r minus 1 general points, then I end up in a situation where my sort of line bundle L minus the sum of these points is actually just has 2 sections. And for a line bundle with 2 sections, the M you get, so that's a pencil, the M you get is just the dual of that line bundle. That's the famous base point free pencil trick. So, and I'm putting so in quotes here because there's a little thinking to do, you end up, if these things are general points, so then you, when you project from these points, you end up with a map to P1, you end up with a pencil, and you'll see that you get an exact sequence. M sub L sits in an exact sequence like this, where everything in sight is a line bundle. So it sits in, so here we have L dual times the sum of all these points. And so this is just the dual of L minus those points, and then we have ML, and then what we end up with here, if you think about it, is just the sum of OC of minus the points. This is ML. No, this is the original ML. And this is actually just M of L minus the sum of the points. So I'm arranging numbers so that this line bundle now has 2 sections. So its M is just the dual of this. Yes, but I've got to do, I'm sorry, maybe I'm blocking it up. The big rank stuff is all over here. So I've got R minus 1 of these things. And so M has rank R. So I've got rank R minus 1 here. Okay. Now, okay, so now I'm in good shape. Because if I have something like this, I can now this implies a filtration of wedge p plus 1 of m with line bundles. So we can now, if we just take wedge products, this gets a filtration. So this gives a filtration of wedge p plus 1 of ml, and then at some point I have to twist by L. So let me do that. So I mean, let's say I want to do wedge 2 of m. So I'd have, there's wedge 2 of m would map onto wedge 2 of that, but coming into wedge 2 of m, I would have this tensor that. So you play this game, and you end up with the filtration of this thing, and there's some pieces, so filtration sort of with line bundle quotients, and some of these terms are pretty positive, and some of them are pretty negative. So let me just say, whose most negative piece is what? So whose most negative piece is what? So I take, I'm going to have L dual twist, so negative pieces is, so R. So the negative stuff is going to look like L dual times the sum of these points. Then I'm going to have to twist by wedge p minus 1, rather wedge p, so I'm wedging 1 down of these guys. And then I twist by L. So this is somehow the most negative. When I take these filtrations, this is the most negative stuff I get. So let's simplify that a little bit. So, so in other words, i.e., the most negative piece of the filtration, I'm being a little bit vague here, but you can kind of do it for yourself. The most negative piece of filtration has the shape, is the sum of things, is a thing, a sum of terms of the form. Okay, so first of all, when I twist by L, the L is going to cancel against the L inverse. And then I take the sum of all the x's, and I'm subtracting p of them. So what I end up with is I have g plus how many x? I have g plus p x's to begin with. So I'm adding g plus p x's and subtracting p of them. So what I end up with here, well, let me write it like this. I end up is with L dual times the sum of all the xi's, tensor OC of minus x. I'm going to subtract p of them. And remember, there are g plus p things here, a tensor L. And so when I do that, what I end up with here, the L's cancel, and I just have a sum of g different points of x. So what I end up with is something of the form OC, let me say xL1 plus xLg. So I just have, the most negative thing I get is just the sum of g points on x. Yeah? I mean, because think about it for a minute. I mean, these other pieces here, just let me, I mean, this is much more negative. I mean, the L dual in this filtration, the L dual, I mean, it's a computation, but the L dual of the sum of those things, that's quite negative. The other is only mildly negative. So the negative stuff is going to involve the stuff in wedge P where I don't forget. I mean, you have to compute, but just trust me, this is what everything boils down to. OK, but now this is good. So now I have a line bundle, but this is now a generic line bundle of degree g on the curve. And this has h1, so this has h1 equal. So how do I kill the h1 of a bundle? So I have a filtration, and I kill the h1 of all the quotients. That kills the h1 of the bundle. So this has h1 equals 0 since the xi in C are general points. So this is a general line bundle of degree g, and a general line bundle of degree g has h1 equals 0. OK, so I mean, this is kind of, it's a very easy thing. You just filter, and the numbers work out. And this is, unfortunately, as far as I know, the one theorem that you can prove like this. You can try to sort of push it, but then the numbers, you kind of lose track. See, the point here is we don't need to worry about maps in the filtration. Just all the pieces vanish. But let me just remark that these are very interesting vector bundles. So let me sort of, I think this is a very interesting question that I don't know the answer to. And as far as I know, I've asked lots of people. So in any event, these MLs control the syzygies of L. So people have been interested in them. And the most interesting cases we'll see next time is when L is the canonical bundle. So let's look at what happens. So this is a, so I'll KC. So then if you think about it, this is kind of immaterial, but anyway, what happens is that then what this ML is, M omega is actually, I mean, you can think of it geometrically as the conormal bundle of a curve and its Jacobian. So that's fun to think about. So I mean, of course, so I mean, it's intrinsically defined, of course, but geometrically it's the conormal bundle of the curve and its Jacobian. Now, what are the invariants of this M? So in general, we have, so the rank of M is, in this case, is just the dimension of the linear series, and the determinant of M is just minus canonical. So in particular, the slope is -2. Now, it's actually quite easy to analyze the stability of these bundles. And I mean, people did this, and maybe it was Ramanan and Paranjape and Ramanan. Paranjape and Ramanan wrote it down first, although people had kind of. Anyway, it turns out it's easy to see, Ramanan, is that these bundles are actually, this M omega is stable as long as the curve is non-hyperelliptic. Okay, so these are stable vector bundles, hyperelliptic. And in the hyperelliptic case, it turns out that you can see there's just a direct sum of copies of minus the G12. So anyway, as long as you're away from the hyperelliptic curve, it's stable, and in general, even in hyperelliptic, it's polystable. But now you see it has integer slope. So let's pick a G minus first root of the canonical bundle. So choose some line bundle A, such that A to the G minus 1 is canonical. Okay, so there's what? 2 to the G minus 1, 2 to the 2. Anyway, there's some number of traces of these things. There's some finite set. And then if we take this M omega tensor A dual, so now this is a bundle. This is a bundle now. This has determinant 0. It has trivial determinant. And it's polystable. So in any event, it's stable in general, I mean, away from the hyperelliptic. So in general, it's polystable. So what does that mean? That means that this bundle comes from a unitary representation of the fundamental group. So this thing comes from well, this thing comes from a unitary representation of the fundamental group of C, right? That's the theorem of Narasimhan and Seshadri. Now, there's a little bit of choice involved because we've chosen this root. So if we forget the choice of the root, what that means is we get a, so in any event you get, so this depends on A, but it depends on A, in a minor way. So in any event you could, it's defined up to some little gadget there. So this is let's say you get a canonical, pi 1 of C, but it's even a little bit to, PSU, or whatever it's called, up to scalars. Okay, so there's a completely canonical representation of the fundamental group, and nobody seems to know what it is. So this is a completely canonical thing. And so what is it? So I've asked a lot of, I think it was really Paranjape and Ramanan that asked this question. So what is representation? I have no idea. I mean, it should be kind of interesting because it's canonical, but the people who do these things don't seem to know what the answer is. So anyway, it's an interesting, so these are quite interesting vector bundles. Well, in some sense it has to, because you get a slightly different thing when C is hyperelliptic than when it's not. But I don't know, I mean, who knows? Who knows? It's irreducible off the hyperelliptic locus, and yeah, so I don't know. It's a mystery. Okay, anyway, so we've proven now Green's theorem. Let's see, how am I doing? Yeah, so let me just quickly, in the last 10 minutes, so this is an old, I mean, Green's theorem is really an old theorem. It's like 30 years old, basically. So then in the intervening time, people have looked at it. I mean, of course, the natural thing to do is to, so I'm supposed to do this lightly, I'm told. The natural thing to do is to ask, how can you extend Green's theorem? So I'm going to quickly mention two such extensions now. And then at the beginning of next time, I'll talk a little bit about Prešky's theorem on abelian varieties. But I'll try to introduce it now. So then the question is, like, what can you prove analogous theorems for other varieties? So other varieties. Well, for example, what's the simplest other variety after curves is projective space. So what about the algebraic property, which property nk does the Veronese satisfy? So Mark Green worked this out. So, I mean, this is elementary, but I was going to prove it, but maybe I won't. So if you take the line bundle OPN of D, so this is the line bundle that defines the d-fold Veronese. So I'm not even sure that this is known in positive characteristic. So this satisfies n sub d. So when d equals 1, you have to think what this means. So that means that, you might think this means that O1 is cut out, but projective space is cut out by quadrics in itself. But what this really means is that there are no higher degree generators. It's a vanishing theorem for the higher degree syzygies. And and then this is used, let's say it's proof using regularity. So again, the picture is as you take more and more positive embeddings, you get this property nk for larger and larger k, and the k that works is linear. But now it's a curious fact that nobody knows. So this is not to say that n d plus 1 fails. So nobody knows exactly what property nk the Veronese satisfies. So remark. So it's known. So Ottaviani and Paletti. So we'll come back to this let's see what happens on P2. So on P2, let's see I hope I have the number right. But OP2 of D satisfies. So the best, it's known exactly what happens. I think it's 3D minus 3. I may be off by 1, but not, I'll have to check. Not 3D minus 2. But it's not known what happens in higher dimensions. So it's known that 3D minus 2 fails in higher dimensions, but it's not known, what happens for Pn. So it's conjectured that the same statement holds for any Pn, but that's very far from being known. So it's conjectured, they conjecture that same statement, the ditto on Pn, but that's not. What is known, again, is that this nk holds linearly and it fails linearly, but it's not known exactly what the best numbers are. Say? Well, no. So I've thought very hard about this. No. So if you mean like with Macaulay. So this will come up in the last class. So I don't know any of this, but I have collaborators who really know how to use Macaulay. So you can work out the syzygies of the 4-fold Veronese embedding, but you can't work out the syzygies of the 5-fold Veronese embedding. It's just too big. So because think about it, the 4-fold Veronese, it's like 60. It's like in what is that? It's that's already in a pretty big projective space, and I would like to work out. There's some conjectures that I'll mention the last time, and you would surely understand, experimentally, if you could do like the 10-fold or the 20-fold Veronese embedding. But you just, that people say you can't. The people who know these things say you can't do that. No. So we'll talk about this. No, it's interesting. I mean, Lawrence and Ein and I had a non-vanishing statement. He had another, as it turned out, non-vanishing statement, completely different. It's quite clear, I think, what the answer is. But there's no evidence for it. But I'll talk about that last time. I think it's really clear what the, I mean, you keep getting the same numbers from different points of view, so presumably, but anyway, nobody can do that. Okay, let's go back to the case of curves. So, so on a curve C of genus G, so to say that degree of L is 2G plus 1 plus P means that we can write L is equal to the canonical bundle of the curve. And let's see, what's left over has degree P plus 3, but your pick is so times something ample. Do I have my numbers right? Yeah. Let me say 2G plus 1. Well, okay, it doesn't really matter. Okay. So you see what these large degree, the way to think about these large degree things is that they're canonical plus a fixed multiple of ample. So the fact that this number is getting bigger with the genus reflects the canonical bundle. So Mukai raised the question. He raised it. I mean, it's a sensible question for surfaces. But anyway, he raised the question is on xn. So you could just extrapolate. Let's see, kx plus p plus n plus 2 times ample satisfy NP. Okay, so this would, of course, be the perfect generalization of Green's theorem. But this is completely out of reach. So in dimensions, so for n greater or equal to 3, this is completely out of reach. Because what would be there, what's the case p equals 0 of this? So it's completely out of reach. Because what's the case p equals 0? Well, the case p equals 0 would be that kx, so when p equals 0, I mean, you can't talk about these properties NP without the thing being very ample. So when kx, this would say that kx plus n plus 2 times ample should be very ample. So very ample. So I mean, you can't even begin to think about the question unless you know this. And this is a famous conjecture of Fujita. Which is very far. I mean, maybe it's kind of known in dimension 3, but this kind of thing is the moment completely out of reach. So you can't sensibly, I mean, these higher syzygy questions, you can't even begin to think about them until you completely understand all these Fujita things. But you can... What? I mean, I think what's a very interesting question is to do the case p equals 0 for surfaces. So for surfaces, one completely controls the, the geometry of these things by these Ryder methods. So in surfaces, I think you could, I mean, I don't even know. I mean, your question is like, is Fujita harder? No, but look, I mean. Suppose you have to stand the rest somehow. Well, but then we could have avoided this morning. I mean, we know after we've read Hartshorne that a line bundle of degree 2G plus 1 on a curve is very ample, but there's still something to do for the defining equation. So I don't know. I mean, I have no idea. On the other hand, there are these interesting new ideas with, that people have, with Bridgeland stability. And you could imagine that these Bridgeland stability questions could say something about, I mean, people who are looking at this could say something about, the like projector normality and stuff on surfaces. I think that would be very interesting. So, I mean, of course, sometimes people prove a theorem that, as we well know, seem totally out of reach. So that's not to say nobody's going to prove this. But at the moment, it doesn't, I certainly have nothing to say. But there is a kind of a, you can say, tweak the question a little bit, and then it actually becomes much more manageable. Okay, so you can tweak the question a little bit. Okay, but you can, however, you can replace, supposing you replace ample by very ample. Then all these Fujita type questions disappear. Then it's very easy to control these things. And then the whole theory, the whole story becomes quite manageable. So this is an old theorem with Ein. So if you replace ample by very ample, then you do get a good statement. So let's let B be a very ample ample line bundle on smooth complex projective variety xn, and then the claim is that then canonical, you actually gain one, n plus 1 plus k times b satisfies property nk. Okay. Okay, and then this uses, so let's see, how am I doing? So maybe so what's fun, what's fun is if you take k equals 0, this is saying that k plus n plus 1 variable is projectively normal, and that's a fun exercise to do. So this uses vanishing theorems for vector bundles, so I'm not going to, it's kind of a little bit grungy. Anyway, but that's what's known on arbitrary x. But now let me just state the theorem I'm going to discuss. I'm not going to prove anything next time, but or at least for this, but sort of state quickly what we're heading, what I'm going to say a little bit about at the beginning of next varieties, next lecture. So let's go back to the case of an elliptic curve. So let's let E be elliptic curve. Okay, so that's, of course, genus 1. So what does Green theorem say? So Green theorem says that if the degree of L is at least what? So 2g plus 1. So that's 1. I'm sorry, that's 2 times, so it's 2 times genus 1 plus 1, 2g plus 1 plus k. So this looks like it's k plus 3. Then L satisfies n sub k. Okay. So you know, degree 4 is cut up by quadrics and so on. So now, of course, you can ask what happens for higher dimensional billion varieties. And the way the numbers always work is that you always get, you don't see the dimension. But in terms of these numbers, every billion variety looks like an elliptic curve, but of course, it's much harder to prove things. So the theorem, you could ask whether the same statement is true in for arbitrary billion varieties. And so that's the theorem of Pereschke. That all, and then it kind of got somehow mechanized a little bit by Popa and Pereschke. So you take x will be an abelian variety of arbitrary dimension. And you take some ample line bundle on x. For example, it could be a principal polarization, but it doesn't have to be. And then the theorem is just this. So then the theorem is that then k plus 3 times A satisfies property NP. NK. So in other words, you get exactly the same statement as you do on elliptic curves, but of course it's a much harder thing. And this is probably the hardest of these. So I'll say a little bit word, but so like what's a special case? So the special case, which actually was only fairly recently, I mean, maybe the mid-'80s or something, it was proven in general after this. So this is this result of Kempfert and Mumford and Kemp and Mumford. So Mumford had a slightly weaker statement, and then Kemp got the, which says that if you do 4 times something ample on a Boolean variety, defines an embedding under which the thing is defines an embedding in which the Boolean variety, the ideal is generated by quadrics. Okay, and then Kemp, after this, had proven kind of a similar statement, but it had a sort of a parasitic factor of 2. And then the good theorem was proven by Pereschke. And so it involves essentially, well, Fourier-Mukai ideas, or as Pereschke calls them, something called the skew Pontryagin paradox. So I'll talk about that, say a word or two about it next time. And then what I want to do for the rest of next lecture, is to go back to the case of curves and discuss some of the fine results for curves. So far, all these results have a kind of a uniform nature. So, you know, for any variety, you get this satisfying NK. For any Boolean variety, you get this, and so on. But one of the original questions of Green was that if you look at canonical curves, you should be able to see geometry in a very precise way in the resolution. And there was another question about the sort of fine structure of embeddings of curves with very high degree line bundles. So that's what I'm going to talk about. I'm going to talk about I mean, now it's now understood exactly which, what the shape of embeddings of curves are with high degree line bundles. And so the funny thing that happens is you start to see geometry. So the fine structure of an embedding of a curve by high degree line bundle is equivalent to knowing the gonality of the curve. So I'll explain that and talk a little bit about what Claire did for canonical curves. So that's the plan for Thursday. Okay, thank you.